The second procedure to compare models is the null hypothesis testing approach. In this approach, we are going to compare a model with a beta 1 of 0 with a model that is different than 0. Now, the procedure is very similar. The first part is very similar to the parameter estimation approach in previous lectures. And although I'm very critical of the null hypothesis testing approach, at least this approach has some rationality which is much better than that of the parameter estimation approach. Remember, in parameter estimation approach, we have to assume a value in the population, and then based on that we make an estimation of that value we assume the value already. So it seems that it's nonsensical to try to estimate something that we already assume its value. So in null hypothesis testing approach, we also assume a value for a parameter, but then we are not going to estimate that parameter value. So we start by assuming that beta 1 is 0 in the population. So in order to illustrate that, I generated this graph by randomly generating numbers from a normal distribution with a mean around 51. So I call it normal 51, and this is to mimic the academic achievement variable that we use in the study, which had a mean of 51. And then I also generated separately random numbers from a normal distribution, a variable that I now named normal 23, which mimics the study hours variable that had a mean of 23. So basically, because I generated those random numbers separately, those variables are not related at all, so there is no connection. And if there is no connection, when we calculate the beta 1 in that population, then it is 0. So you have to imagine these, that they are not just 300 values. This is millions and millions of values. So of course, with millions, values would be stronger, but be busier than this. But this is just an illustration. And here I'll illustrate that we've got a flat beta 1. So beta 1 is 0 in the population. Okay. So from that population with a beta 1 of 0, we obtain a sampling distribution of beta 1. That's the same as what we did in parameter estimation. We obtain the sampling distribution of the parameter we were interested in. So here we do the same, and so how do we do it? We obtain a sample from this population, the same size as the sample in our study, which is 300. And we calculate the mean. No, we don't calculate the mean. We calculate beta 1 in that sample. So we've got 1 beta 1. So we obtain 10,000 samples, and we calculate the beta 1 10,000 times. So now we've got 10,000 beta 1s. So with these 10,000 beta 1s, we generate a distribution of beta 1s, and that distribution will be around 0 because it comes from a population that has a 0 beta 1 of 0. So the mean of that distribution will be 0. The standard error of that distribution, which is the standard deviation of that distribution, it's a bit complicated, and so we here have the way we refer to it as SE of B1, but it has a formula that I'm not interested in explaining here. But what we typically do is, instead of doing a sampling distribution of beta 1, we use the t-distribution. Okay. Now, this is again something that I dislike. The reason why we use a t-distribution is a historical one, because we know very well the t-distribution. We know the normal distribution very well. We don't have to do samples to generate normal distributions or generate t-distributions. We know them. In the past there were tables that would tell us the probability for each value for t and for each value z value in a normal distribution, and etc. So because we know these distributions very well, we in order to avoid calculations, then we transform everything to a z-score or to a t-score, and then we use the t-distribution. But why do we do that when we can easily create now, with the computational power that we have, a sampling distribution of beta 1 easily? Okay, so that's why I don't like to continue using things, because they were used in the past a lot. But anyway, basically the idea is that you can manually construct a sampling distribution of beta 1, or transform beta 1 into t, which is step 3. So in step 3 you calculate the beta b1 in the sample, or calculate the t by using b1 divided by the standard error of b1. And then the next step is to consider the sampling distribution, and in that sampling distribution, which could be a sampling distribution of beta 1 or b1, and or if we transform what we calculate, the b1 we calculate in our sample into a t-score, then we look at the t-distribution. And basically in this study, I think the t-score is 18. So basically the next step is to say how likely is the t that we obtained in our sample, which was 18, how likely is to find that, or a more extreme value, in this distribution, in this t-distribution. Well, you can see that 18 is very far from here, so it's going to be very unlikely. And even values above 18, or when we use the hypothesis that we use here, I mentioned before, was that we are looking at alternative hypothesis that beta 1 is different than 0, then we have to look at the two tails of the t-distribution. And if we look at the two tails of the t-distribution, then we have to look at 18 or more, or negative 18 or less. And even though we've got a large way until infinity for two sides, the probabilities are really, really, really small, because after 3 standard deviations in the t-distribution, the values are very, very unlikely. So the 5th step is now, by the way, that value was the probability of obtaining the t-score or a more extreme value in this distribution, in this t-distribution. That's the p-value. So that's where the p-value comes from. And the 5th step then is to determine whether that p-value is less than a threshold. And a threshold that has been very popular is 0.05 or 5%. And so if it is less, that p-value we calculated is less than that threshold, then we reject the hypothesis that the B1 we obtain in our sample comes from a distribution with beta 1 equals 0. And that's the null hypothesis testing approach. We hypothesize that a null parameter in the population, so 0 here, beta 1 equals 0, and then we say, oh, how likely it is to find the value we obtain in our sample if the beta 1 in the population is 0. And because it's very, very unlikely, then we reject the idea that it comes from a population with beta 1 equals 0. So we support the idea, but we don't prove, we just support the idea that it comes from a distribution, from a population in which beta 1 is different than 0.